Hello guys, so welcome back to another video on my channel. In the last video, I started making a series on the UK Integration B 2024-2025 round 1. I did the first 10 questions, and in this video I'm going to do the next 10 questions. I remind you, in all there were 30 questions, so there will be another video after this one to cover the final 10 questions. So let's get started. Question number 11 is integral, which I'll call I, from 0 to infinity, si of x times sine x divided by x dx, where the si of x is something we've encountered in the past. It's the sine integral function. So sine t over t dt. Maybe I should move this down. Okay. Now, what we notice from this is when we differentiate this definition of the sine integral function si of x, we get sine of x over x. So that means that si of x is the antiderivative of sine x over x. And with that knowledge, we can go ahead and use integration by parts. So when we do that, we have to take the antiderivative of the sine x over x, because we know that is just the sine integral function si of x. So when I do that, I have si of x, which is untouched, and the antiderivative, which is integral 0 to x of sine of t over t dt. All of this evaluated from 0 to infinity minus integral 0 to infinity. Now we have to differentiate the si of x. When we do that, we have sine of x over x and integral 0 to x sine of t over t dt, which comes from the antiderivative part. And we have a dx that's outside. So let me just make a little bit of space for that differential. So in the first term, we have si of x, and this is also an si of x. So we get si of x, the whole squared, minus, here we have integral 0 to infinity, si of x from this second term, times sine of x over x dx. So notice the second term is just I. So we just have si of x, the whole squared, minus I, giving us 2i is just, sorry, we have to evaluate this from 0 to infinity as well, because it's a definite integral. Si of x squared from 0 to infinity. So at infinity, if we go back to our definition, at infinity we have integral 0 to infinity sine of t over t dt, which we know is the Dirichlet integral that has the value pi over 2. So that's pi over 2 squared minus, well, when we plug in 0, we have integral from 0 to 0, which is just 0. So in the end, after simplifying everything, I is just pi squared over 8. That's it. That's how we solve number 11. Moving on to number 12. For number 12, we have integral minus infinity to infinity dx over e to the x plus e to the minus x plus 2 squared. Now, as soon as you see two exponentials with a positive and a negative exponent added together, you should remember the hyperbolic trigonometric function. So e to the x plus e to the minus x over 2 is just cosh of x. So e to the x plus e to the minus x is 2 times cosh of x, and we are going to use this fact in the denominator. So when I do that, I will have 2 plus 2 cosh of x the whole squared. Now I can use the fact that we have a 2 multiplied. We can pull that out, and that squares to give us a 4, 1/4 integral minus infinity to infinity dx over 1 plus cosh of x the whole squared. Now we have another identity we can use. 1 plus cosh of x is 2 cosh squared x by 2. This is kind of similar to the regular cosine double angle formula. And the advantage of doing that is we have 1 over 16 now from the overall factor of 2 dx over cosh squared of x over 2 the whole squared, which is just 1 over 16 dx over cosh to the 4th of x over 2, which we can actually rewrite as secant to the 4th, secant of h to the 4th power x over 2 dx. We can break the secant up into secant h squared of x over 2 times another secant h squared, which we can write as 1 minus tanh squared of x over 2. Now, this is sort of counterintuitive because we know 1 plus tan squared of x is secant squared of x. Here we have a minus because they're hyperbolic trigonometric functions. And we can also do the substitution u equals tanh x by 2 because du is nicely 1/2 secant h squared x by 2 dx. So we have 1/8. Now the bounds, since the hyperbolic tan is basically sinh over cosh, which looks in terms of exponentials something like this. We notice that at negative infinity, we just have -1, and at positive infinity we have a 1, and we have 1 minus t squared dt, which is very nice to integrate. So 1/8 t minus t cubed over 3 minus 1 to 1, which is 1/8 1 minus 1/3 plus 1 minus 1/3. If we evaluate all that, that's 1/6, and that's the answer for number 12. Moving on to number 13. So number 13 is integral 0 to infinity sine of x plus sine of 1 over x divided by x times 1 plus x squared dx. Now noticing the structure in the numerator of a function added to its argument in the reciprocal, we can try to do u equals 1 over x, a reciprocal substitution. Du is minus 1 over x squared dx. So that gives us 0 to infinity again, sine of u plus sine of 1 over u divided by 1 over u 1 plus 1 over u squared. And we have a 1 over u squared, or rather just the u squared, from the differential factor du. And when we rewrite this, we get integral 0 to infinity u squared sine of u plus sine of 1 over u divided by u times 1 plus u squared du. And when we add the integral in x and 1 in u, and we can just change u back to an x because it's a definite integral, we get 0 to infinity x squared plus 1 sine of x plus sine of 1 over x divided by x times 1 plus x squared dx. So the x squared plus 1 cancels. We have sine of x, sine of 1 over x, all divided by the x. And we can break this up into two integrals by linearity. So we have sine of x over x dx plus 0 to infinity sine 1 over x dx. The first integral we know, the Dirichlet integral, is pi over 2. Plus we do get a similar integral by doing a reciprocal substitution. So you get integral 0 to infinity sine of x over x dx. So that's two Dirichlet integrals. So we have pi over 2 plus pi over 2, which is pi. And that was 2I, if you remember correctly. So that means my I is just pi over 2. And that's the answer for number 13. Number 14 now. Integral 0 to 1 tan inverse of x to the n over x dx. When you notice arctan of some variable divided by x, a very good strategy is to consider the infinite Taylor series for the arctan. So sum from k equals 0 to infinity, integral 0 to 1 minus 1 to the k x to the n, whole thing to the 2k plus 1 power, divided by 2k plus 1 dx. And then sum from k equals 0 to infinity minus 1 to the k over 2k plus 1 integral 0 to infinity x to the 2nk plus n minus 1 dx. I'm just simplifying using the properties of the exponents and things like that. And then integrating this is just use the power rule of integration. Minus 1 to the k over 2k plus 1 x to the 2nk plus n over n times 2k plus 1 from 0 to 1, which gives us sum from k equals 0 to infinity minus 1 to the k over 2k plus 1 squared times 1 over n. The 1 over n is unconcerned with the sum, because the sum here, the infinite sum, is actually just the Catalan's constant. So the final answer is Catalan's constant divided by 2 by n, sorry. Okay, moving on. Question 15. Integral 0 minus 1 to 1 sine square root x divided by sinh square root x plus sine square root x dx. Now we can use a King's property. X goes to minus u, noticing that sinh of x is minus I sine of ix, and sinh of ix is I sine x. When we do that, minus 1 to 1, we get sine of square root of minus u. So now square root of minus 1 can be taken out, which becomes I. So I times square root u. Same thing with the arguments of the functions in the denominator. So sinh I square root u sine of I square root u du. Now we can use the relation between the sinh and the sine. We get I sinh square root u divided by I sine square root u plus I sinh square root u du. We can cancel the I factor from everywhere. And notice that when we add two of those together and maybe change the u to an x again, because it's a definite integral, get integral minus 1 to 1 of just dx, because the numerators will cancel exactly with the denominators, which has value 2. So that means I is just 1. That's a very, very neat answer. Now moving on, and trust me, if you think some of these are quite easy, there's better questions coming up. So question 16, integral 0 to infinity e to the minus px squared minus e to the minus qx squared divided by x squared dx, where p and q are greater than 0. Now there's many ways of doing this. You could force a Frullani here by introducing some other exponential between. You could use Feynman, which is probably the most sure shot method if everything else fails, or try a more elegant method that I'm going to show you. So notice integral from q to p of e to the minus tx squared dt is minus e to the minus tx squared over x squared from q to p, which turns out to be minus e to the minus px squared minus e to the minus qx squared over x squared. So we have the same thing in the integrand here. It's just that there's this extra minus sign. So we have integral from 0 to infinity that was outside, and we introduce the separate integral from q to p, the minus e to the minus tx squared dt dx. We can use the minus to flip the bounds of q to p to go from p to q. Integral 0 to infinity, and I also interchange the integrals e to the minus tx squared dx dt. When we integrate with respect to the x, this is just a Gaussian integral. So that's half the Gaussian integral, so square root pi over 2. Along with, we had that square root t factor because we had a tx squared in the exponential. So integral p to q 1 over square root t dt, which is very nice to integrate again. We have square root pi square root t from p to q, which gives us square root pi square root q minus square root p, and that's the final answer. See, that's the nice method. You do it really fast. Moving on, question 17 is probably one of my more favorite questions. Integral 0 to pi over 4 plus 1 tan of x minus tan of x minus and so on. So it's a infinite nested function. So when we have functions like these, the first thing is to do is to set y to be the integrand, that infinite composition of functions. To notice that y is just tan of x minus y, because we see that infinite pattern again inside. And again, so x is just arctan of y plus y. And with this, in this substitution, we have to find the upper and lower bounds. So the upper bound is when x is pi over 4 plus 1 equals arctan of y plus y. When does that happen? It's kind of evident from this, is y equals 1. And for 0, it's again evident that y has to be 0. Then comes the question of the differential. You can differentiate both sides. So dx is going to be 1 plus 1 over y squared plus 1 times dy. And that's it. That's all we need to transform our integral into something more palatable, something that we can solve. Integral from 0 to 1, y from the integrand itself, 1 plus 1 over y squared plus 1 dy from the differential, which is easy to solve. This is y squared over 2 plus 1/2 natural log of y squared plus 1 from 0 to 1. At 0, everything vanishes, so let's not bother with that. We have 1/2 of 1 plus natural log of 2. That is the final answer. Now, question 18 is kind of repetitive. If you have been on my channel, it is super repetitive. But if you haven't, maybe I'll do it real fast for you. So ln sine x dx from 0 to pi over 2. Let's use King's property. So we have sine of pi over 2 minus x dx. And when I mean King's property, I say x goes to pi over 2 minus x in this case. And that is just integral 0 to pi over 2 natural log of cosine x dx. So we add both of those. So 2i is integral 0 to pi over 2. Natural log of sine x plus natural log of cosine x is natural log of sine x times cosine x. We can use the double angle formula for the sine to give us natural log of 1/2 sine 2x dx. Break this down using the product to sum formula of the natural log. So we get natural log of 1 over 2 integral 0 to pi over 2 dx plus integral 0 to pi over 2 ln sine 2x dx. We get minus pi over 2 times ln 2 from the first one. From the second one, we do a nice trick. Set 2x to x. Gives us a 1/2 factor. Integral 0 to pi in this case. ln sine of x dx. And we'll just work with this second integral here. So we can break the integral from 0 to pi over 2. ln sine of x dx plus 1/2 integral pi over 2 to pi ln sine of x dx. And in this second integral, we can again introduce x goes to x plus pi over 2, so that we get 1/2 integral 0 to pi over 2 ln cosine of x dx, which, if you remember, is again our original I. because this using King's property was ln cosine x from 0 to pi over 2, which is exactly what we have here. So this is already I, this is 1/2 I already, and then the cosine part of it is another 1/2 I. So that's 1 full I in the second integral. So we have, the equation is 2I equals minus pi over 2 ln 2 plus 1 whole I, right? Because this was the first factor. This got broken down into two, 1/2 I and another 1/2 I, which was a full I. And we just solve for I, which is minus pi over 2 ln 2. It's a very nice result that we've used countless number of times on our channel. And now the last two questions to be covered in this video. Question 19, 0 to pi over 4, arctan of 1 plus tan x over square root 2 dx. Now, this property of using symmetry in this case is not really obvious to people, but if we use King's property, so arctan of 1 plus tan of pi over 4 minus x over square root 2 dx, we just get, using some identities from trigonometry, that tan of pi over 4 minus x is 1 minus tan x over 1 plus tan x. We get integral 0 to, sorry, this should be pi over 4 rather than pi over 2, arctan 1 plus 1 minus tan x over 1 plus tan x, all of that divided by square root 2, maybe put a bigger bracket on it, dx, and we can simplify all of this nicely. Tan inverse of, once we simplify this becomes 2 over square root 2 times 1 plus tan x dx, which can be further simplified. Tan inverse of square root 2 over 1 plus tan of x. And this is the point where we actually stop and realize that if we add both of these things together, so we have 2I, we add both of them together, 0 to pi over 4 of tan inverse 1 plus tan x over root 2 plus tan inverse root 2 over 1 plus tan of x, trying to give myself that extra space, dx. They're reciprocals of each other, and we have the nice property, when you add reciprocals of arguments in two inverse tan functions, you just get pi over 2, as long as x is greater, the argument is greater than 0, and the argument is greater than 0. From 0 to pi over 4, 1 plus tan of x is greater than 0 dx. So that just becomes pi squared over 8, and that's 2I, so I pi squared over 16. Perfect. The last question, which is probably the more challenging question in this video. Integral 0 to 100 x to the fractional part of x minus 1 ln of x to the x plus fractional part of x dx. Now we can do what we usually do for these fractional part integrals. Sum from n equals 0 to 99, because we are going to have to split from n to n plus 1 so that we cover all numbers. And we have x, the fractional part is x minus the floor of x minus 1, ln of x to the x plus x minus fractional, floor of x dx. Now the purpose of discretizing the interval was that now the floor function on this discrete integral is just n, and we can bring the power of x down, so x times ln x plus x minus n. We're not done yet. We can pull one final trick. X goes to x plus n. When I do that, sum is the same, the bounds are from 0 to 1. We have x plus n to the x minus 1. We have x plus n ln x plus n plus x dx. And now this is where we actually, and this is the harder part of this problem, is to notice these things in the time we have to solve these questions. Y equals x plus n to the x. So when you take ln y, you got x ln x plus n, and when we differentiate, we get 1 over y dy over dx is ln x plus n plus 1 over x plus n. So dy over dx, x plus n to the x minus 1 times x plus n ln x plus n plus x, which is exactly the term we have here. So that the term inside this integral is a complete derivative, is the total derivative of y, which is x plus n to the x. So I is just sum from n equals 0 to 99 of x plus n to the x from 0 to 1. So that can be easily evaluated. It's n plus 1 minus 1. So that's sum from n equals 0 to 99 of n. So that's the first sum of the first 99 positive integers. So that's 4950. You can use the arithmetic progression formula for this. But that's the final answer, and that's it for this video, guys. Please let me know what you think by sending me an email, because I've disabled all comments. But see you in the next video. Peace out and have a nice time.